来了。4 4 30. Hmm. Oh, okay. So we are right introducing the empirical distribution function. Okay, very good. So basically, what's the idea? Let's quickly refer back to where we discuss where we were uh, stopped from last time. So we have two samples. Okay, we have the sample x and y. Okay, and here we have the null hypothesis that they are actually following the same distribution. So that's our H0. So instead of looking at the means or a particular statistic, here we're looking at the entire distribution. Okay, so basically we assume that the distributions are the same. And here we would actually assume that the CDFs that of the two samples are the same. And eventually, we would like to see if there are sufficient amount of evidence, okay, to counter, okay, to disapprove this underlying assumption. So notice, uh, just to quickly look at what we were discussing, it's possible that certain distributions will not have a very good PDF or PMF, but the CDF, okay, the cumulative distribution function always exists. So we would somehow try to sort of generate an estimate of the CDF from the sample. So that's what we are heading towards to. Okay, so we can start by defining the empirical distribution function. So what's the idea? So the idea here is that remember, when we have a CDF that we want to approximate, it's f of x. For different x value, there will be a different uh, value of the CDF, which represents what? Which represents the probability of the random variable, or you can say the random sample xi is upper bounded by x0. Okay, so that's the way that CDF is defined. But then remember, this is what? This is the proportion, right? This is the probability of the sample less than equal to x0. So this is essentially you can manage, you can try to do the computation, okay, to approximate by what? By this ratio, okay, empirical ratio of how many samples are in fact at most x0, and then we divide by the total number of observations. So that's giving you a ratio. Okay, so this is the ratio. Basically, you are basically counting. Here we have a bunch of indicator functions. So whenever your xi sample is upper bounded by x0, then we're gonna indicate it as one. Otherwise, it's gonna give you a zero. Okay, so that's exactly you sum these up. That's exactly counting the number of uh, samples at most x0, right? So this is a very good estimator. So this is what we were discussing. Okay, I think so. Basically, later this week we're gonna assign the new homework, and some of them are gonna relate really closely to what we have established from before. So basically, the things the material after homework one up to this point. So there will be certain um, questions regarding certain distributions and the counting. So that's something you can look forward to. All right. So now basically we use for every x0, okay, this kind of ratio to estimate. So this is of course there will be infinitely many x zeros, but then rely on data, you will be able to construct this kind of approximation. Okay, that's the estimator. Okay, now for every x zero, we are able to find a uh, ratio, right? We can use such a quantity as an estimator. So the estimator of the CDF f of x is, we're gonna use the same notation. It's gonna be f hat of n, f hat sub n. So here f hat, this is the exact same notation. So uh, here n's, the subscript indicates the number of observations that you see. Okay, and f hat is basically a typical notation for empirical approximation. Okay, put it on the left hand side since it's gonna be in the middle of the way. All right, this estimator this estimator is called the empirical distribution function. Okay. So actually, if you go ahead and look at the book about which is named All of Non-Parametric Statistics. So that book actually begins with this material about empirical distribution function. But then regarding to those tests we have already discussed, some of the tests are elaborated in the latter part of that book. Some of the tests are only discussed in the red book. It's a little bit more applied. So for certain topics, indeed, we would have to somehow uh, go back to jumping between books. So, but of course, for this topic right here, you are welcome to basically look at the uh, purple book, well, that's named as all of non-parametric statistics. All right, so this is the way that we approximate. So yeah, you can see that below there's going to be a figure. So we're going to utilize that later. But basically, that's the way that you approximate the CDF, well, given data. Okay, so example. Of course, when there's a lot of data, it's gonna get a little bit more complicated. But if we do not have many, if we do not have many uh, uh, samples, then the values is sort of limited. So we can expect it's kind of like a step function behavior because you are essentially saying, okay, what's the proportion of your sample less than or equal to a fixed value, right? So if your x0 is larger than every sample, then that's gonna be a proportion of one, right? So if none, then it's gonna be a proportion of 0 over n. So, but the denominator is always n, the numerator is always an integer. So at most, there's gonna be n plus 1 steps. So the smaller n, the simpler the function is. Example, mm, 5 observations. Let's say 1, 1.2, 1.5, 2, 2.5. So now here, basically, you can see these are 5 well samples they're gonna be the separations, right? They're gonna be the breakpoints of your definition. So less than one is gonna be none, right? So and then less than 1.2, larger than one, there's gonna be one, okay? And then less than three, that's all of them, right? So basically these are the breakpoints. So even though x0, okay, can be arbitrary, but we don't really need that many. You don't really need all real numbers to represent this function. That's the key. Okay, so I still need a bit more space. So let's go a little bit further, a little bit further away. So five observations. Example of EDF, empirical distribution function, is below. So, okay, so just like what we discussed, we have 1, we have 1.2, we have 1.5. So, 2 is here, 2.5 is here. So basically, you try to make the illustration good enough. Okay, so now you remember x0 is upper bound. Okay, it's includes the sample value. So basically, let's just count. Okay, when let's say when x0 is 1, all right? So one sample is at most 1, right? So that's right here, one fifth, and uh, let me see, one, two, three, four. Okay, so yeah, let me make it a little bit taller. Okay. So I'm just using the vertical strips to somehow represent the height. So this is one fifth, two fifths, all the way, three, four. This is one. All right. So okay, now when x0 is less than one, then clearly no data is less than one, right? So this is gonna be a solid of zero. So here, that's my zero. Okay, that's zero. So here I'm making this sort of like a distinction from the horizontal axis. So be aware. And then when we were at 1.2, okay, there will be two at most 1.2, and of course for larger values it's the same thing. So it's going to be like this and like this, and then this, and then this. But here it's open circle here, open circle here, open circle here, open circle here, and all the way to the right. Right? So this is our EDF, okay, of X. Or you can say this is F sub n of X hat. Right? Here, of course, n here is 5. Mm, all right, so that's pretty straightforward. So here, there are 5 jumps, each located at the position of the observation, right? So each observation here gives you that jump. So basically, at every observation, your probability of less than or equal to that amount is going to jump from the left to the right. Okay, so that's really up to the distinct values out of the observations. Now here, every one of them is distinct, so we have a total of five. But of course, if there are the repetitions, you would have something a little bit different. So at the positions of an observation, moreover, the height of each jump is same as 1/5 because we have no repetitions, right? We have no repeated observations. So constructing this kind of EDF, I would like to say that here, since the data they are sorted, okay, since data are sorted, then the construction will be relatively easy. But if if the uh, list is not well sorted, then you would have to do something to sort it in order to construct the EDF out of the data. And we definitely would need to do a few such questions so that we can get familiarized with this kind of procedure. But of course, when more observations are used, we're gonna see nicer approximation of the CDF. So this okay, that's good. So that's the figure we're gonna look at. So this is the not another example. The following provides a case of EDF versus versus CDF when n equals to 100 or 1000 are generated. Okay. From standard normal. Right. So basically, these red curves right here that you see in the figures. So let me zoom up a little to see a little bit more clearly. Okay. So the red curves right here, these are the same thing, which is the underlying distribution represented by the CDF. So clearly, you have this kind of monotonic curve that's actually having an asymptote of 0 here and 1 here. All right. But then if you're now constructing all these 100 data, so essentially, what do you see here? You see in black, that's the empirical distribution function. So you have what? You have 100-ish steps. So basically, still really similar to what you have seen above. So the smallest data point, okay, on the left-hand side, you will just have a horizontal 0. And then each distinct and larger sample value will you push the probability upwards. And then the proportion just goes up and up. Every time it's a multiple of 1 over n. So this is sort of like the reason why it's kind of like a zigzag. Every time it slightly increases vertically up, right? So you can sort of expect that, okay, this is where the smallest data occurs, which is like negative 1 point something. Okay. And then basically just sort of like the trend indeed is following the red curve, although it doesn't match that well, right? So this is the error for approximation, of course. And of course, if you're using more data, right? So if you're using 100 random samples, then the fitting actually is rather close. Okay. So now the black one is still this kind of zigzagging. So it looks like the smallest value here is like close to -3, right? But then you see this uh, indeed this kind of approximation. If you think about it, it actually still follows a certain type of law of large numbers or central limit theorem result. We will of course elaborate clearly as follows, but now you get the idea. Okay, so when you have a sort of underlying distribution, no matter what that is, essentially point-wise, okay, this function in black is gonna get closer and closer to the function in red. So that's what's called the empirical uh, approximation. Okay, this is the empirical distribution function. Okay, so here the red curve indicates the true CDF of the standard normal, okay, the underlying distribution when sample size is large, the EDF is pretty close to CDF, to the true CDF. All right. So now, basically, as long as you have a sufficient amount of sample, then essentially you will be able to utilize the sample to in a way approximate your underlying distribution, right? And then later we're gonna think about using two samples, okay, to respectively construct their respective EDFs, and then that will be utilized, right, to further conclude whether these two samples are actually following the same underlying distribution or not. Okay, so those are going to be utilized to help with inferences and hypothesis testing. So, but before that's the high level idea. Any questions so far? So the high level idea is just construct the approximation of the distribution following data, right? So let me also type the question here. So any questions so far? So you guys can hear me, right? So yeah, just to make sure that I'm not there's nothing wrong with the internet or the Zoom setting or the device. Yeah, well, if the thing works, then you guys can do reactions like thumb up or I think this is what's called the reaction with effects. Okay, very good. So yeah, the emojis with effects that looks pretty interesting. You may want to test to get ready for whatever future meetings that you may join. All right, so that's the idea. Not really complicated. Okay, so now let's continue with the properties before we get into the uh, testings. Okay, so now 2.1 properties. So actually, the EDF follows, it has really nice properties. Okay, so because EDF is the average of the random variables, that's indicator of xi less than equal to x0, uh, less than equal to x. So basically, we have, you can say this each xi, remember each xi is a random sample, or you can say is a random variable. And now the indicator is kind of like an outer function of this random variable. It's of course a non-random variable. All right. Now here we're actually taking the average of n of those, right? So that's a sort of like a sample average. So we can just study each of these random variables. So now let's denote that indicator as y. Okay, so let's denote yi as the indicator of xi less than x. So um, to examine what yi does, see the breakdown. Okay, so remember this indicator function only returns two values. So yi equals to either 1 or 0 when it returns 1 when what? When xi is less than equal to the scalar value x. Otherwise, okay, if the sample is greater than x, then I return 0. So yi only takes values 0 and 1. So it is actually what? It's actually a Boolean variable. Okay. Excuse me. Not only is Boolean, but it's also Bernoulli. Actually Bernoulli. Actually. So remember, a Bernoulli random variable has a probability as a parameter returning 1. Okay, so um, that's where I need a proportion to, yeah, so let me write it down. It has a parameter P that determines the probability of outputting 1. And now if you think about it, it's actually really easy, right? So here we care about the probability of this occurs, which is what? Which is actually the CDF of xi, right? The probability of xi, let's equal to little x. So P here, P equals to the probability of yi equals to 1. Let's be really explicit. Now it realizes 1, so that means we need the event that xi less equal to little x, and which is f of cap f of x. Okay, the CDF. Okay, for every x value, we actually look at the CDF uh, of my random variable to indicate this probability here. This means what? Thus, for a given x, okay, yi follows the Bernoulli random variable with f of x, this value, as my success parameter, okay, success probability. Now, given this, we'll be able to compute many things, right? The expectation and the variance. So this implies that the expectation of yi is the expectation of the indicator, which is here, of course, if you just check the uh, formulas of the Bernoulli, right, from lecture 0, that's actually going to be P, okay, which is f of x. Okay. But now if you ever want to compute the uh, expectation, what do you need? You just need, okay, the random variable value 1, that's multiplied by the probability, which is uh, P of xi less equal to x plus 0 multiplying by the complement, right? So now the second part, I'm writing it in a relatively squeezed way because, well, actually it doesn't do anything, but of course, for the completion. So that's what we should know. And now remember the variance is also easy to calculate. Variance of yi is actually what? It's actually the expectation of yi minus. So here, remember, although the formula is this way, but you also realize that this is the expectation of y squared minus the expectation of yi whole thing squared. Okay. And now if you think about it, when yi is a binary output, then yi squared has the same thing as yi. So um, for the probability of whenever yi is 1, then yi squared is also 1. When y is 0, the y squared is also 0. So that thing actually is the same from my expectation from above. Okay, so this equals to f of x minus f of x squared. All right, so these two have the same values. This thing equals this. Okay, so that's what we should be very familiar with. So this is exactly the reason why many people would just write f of x, y minus f of x to indicate the variance here. It's just so it's nothing special, just Bernoulli. But now I just realized that okay, we have x fixed. That's gonna give you the computation. But then of course we are now looking at the sample average. Okay, so that's even more simplified. So this is for given x. Okay, just remember we need to fix x first in order to do this calculation. And now about the empirical distribution function. Okay, recall fn hat equals to the average of all these indicators. All right. Okay. So this is actually we have independent xi's. So these are also these circled indicators are also independent. So you actually have a sample average with independent samples, which is exactly the average of y1 through yn. Okay. Then we know actually for this kind of uh, IID. Okay, so these are IID, independent and identically distributed. So here, this sample average is unbiased. Okay, so you know and this equals to the expectation of yi, which is the same from above, and the variance of. So this is something you have done from the previous homework, or at least you are expected to calculate this. Basically, when your variance is something, then the sample average has the variance as one over uh, the sample size, okay, times the original variance. So it should be okay. Well, just remember it's going to be just if you want to split, okay. So we have what? We have this to be the sum of y of n. So if you take out this denominator, it's going to be 1 over n squared. And now the independence will be able to distribute this variance into individual ones. So this is indeed 1 over n times the variance of yi, which is also a function in terms of of f. Okay. And of course, then we are able to go further, okay, using things like central limit theorems. So what does it tell us about using uh, EDF as an approximator and as an estimator of CDF? First, at each little x, fn f hat of n, f hat sub n is unbiased because the bias is defined as the expectation minus the true value of my statistic. Okay, so but if you refer to this line, it's zero. Okay, unbiased. Second, now if you look at the variance here, it's getting less and less. Okay, so just by looking at the formula right there. Second, the variance converges to zero as n approaches infinity. So now, think about the lemma that we emphasized at the within the lecture zero. When your variance converges to zero and the bias converges to zero as two separate sequences, okay, then we have what's called the convergence in probability, right? So lemma O3. This implies that for given x, okay, is pointwise convergence in probability. So Fn, f hat of n, f hat n is a consistent estimator, okay, of the CDF. So that's the convergence in probability. And of course, now remember we are able to also utilize central limit theorem to get an estimator that's so this is convergence to probability. That means what it means. Now the variance here is diminishing. Okay, it's getting closer and closer to zero. But now if you compensate, okay, by multiplying square root of n in the central limit theorem fashion, then you actually will get something close to standard normal. So in addition, the EDF also ha has the following central limit theorem feature for given x. So here we are able to state that the uh, remember, so E uh, EDF right here is essentially this kind of sample average. Okay, the sample average follows the central limit theorem minus the true mean multiplying by square root of n actually converges in distribution to the normal with the zero mean, and now the variance actually goes from here. Okay, for each random variable. All right. So basically, the approximation error, okay, even if you scale it by square root of n, okay, so scaling it by a number that's growing larger and larger, but the variance in the end is the same. So still, this is another way of seeing what we discussed from above for a diminishing variance, central limit theorem. Okay, namely, the EDF is asymptotically normally distributed around f of x with a smaller and smaller variance. And of course, if you think about this kind of variance, uh, actually at the end, right, when f is close to zero or close to one, this product is actually small. So the problem really occurs when your f and 1 minus f, they are rather close. So if you think about what's going on in the middle of the graph, okay, so that's somehow happening right here. So in the middle portion, okay, in the middle portion, so that's where your 1 minus f and f have a rather large product, okay. Near the end, okay, those regions, either your CDF is close to zero, so the product is zero, it's nearly zero, or when that 1 minus f is nearly zero, then the product is still zero. So those will be the regions where variances are really small. But the variances gets larger, so that you will see this kind of deviation from the true mean. All right. And of course, now notice when n gets, now you see 10 times from before, then actually what the variance actually uh, reduces up to 3 points, the square root of 10, right? So when n multiplied by 10, so the square root of n is 3.3 ish. So that kind of deduction indeed shrinks the deviation to a much smaller scale. Okay, so now visibly, you cannot really distinguish the change. Okay, so that's the power of EDF. All right, pretty standard. Okay, nothing surprising. So examples. Assume we have x1 all the way up to x100. They follow some distribution with cap f being the CDF, okay, where cap f is a uniform distribution over the interval from 0 to 2. Okay, here are our questions. Firstly, let me draw a small line to indicate the item. Okay, what will be the expectation of the EDF at zero point 0.8. Okay, so now let's just do the calculation. So remember, just think about the properties of this EDF. The expectation will be the true PDF, excuse me, true CDF. Expectation equals to f of zero point 0.8. Okay, so now remember what is CapF. CapF is the probability of the random variable at the most is the input of your function. So x less than or equal to zero point 0.8. Okay, so now here we just integrate, right? So we have the integral from 0 to zero point 0.8. So here we have the uniform distribution from 0 to 2. So it's going to be 1/2, and then dt. Well, here we have x, then we can use that little x, that's fine. But basically, you have 1/2 uniformly in the interval, but now you integrate from 0 to zero point 0.4, excuse me, to zero point 0.8. So that's what? That's 1/2 x, okay? Evaluate at 0 and zero point 0.8. So that's zero point 0.8 over 2, which is zero point 0.4. All right. So now, what will be the variance of this approximator? So remember, the sample is 100, so it's going to be a division there. Just utilize the formula we have established earlier. Okay, so the variance is where? Is here. Okay, so the probability is already computed. It's zero point 0.4. So this is f of zero point 0.8 times 1 minus f of zero point 0.8 to be a little bit more careful about the steps so that we are on the same page. So zero point 0.4 times 0 0.6. So that's what? That's 10 to the negative 2 in the top, and then 10 to the negative 2 it resulted from the division. So it's what? 24 over 24 times 10 to the negative 4 is 2.4 times 10 to the negative 3. Okay, so that's very small. Remark. So a quick conclusion that we can observe from before. We know EDF converges to CDF in probability. So the above analysis also tell you that for fixed x, so yeah, let's just use words. For given x, we have this difference actually converges to 0 with in probability. So earlier we said the former, okay, the sample average, the EDF converges to the CDF in probability. And of course, if you slightly modify the statement, it's going to be that the difference is convergent, okay, to 0 in probability. Now, why is it important? So remember, for each x, this sequence actually converges. So with some additional assumption, actually this convergence can be uniform. So here, let's be very careful. So in calculus or in real analysis, when you think about pointwise convergence, you cannot really guarantee what's called a uniform convergence. But uniform convergence is much more strong, much stronger, but also very much more useful. So this is related to what's called the pointwise convergence in analysis. We can extend it to uniform convergence. That's a theoretical establishment we're gonna omit for the course. Okay, we can extend this result to a uniform convergence. Uniforms. So that's not exactly a uniform convergence. So the sense is the same thing. So now, instead of converging to uh, 0 for every x, okay, I'm gonna say the supremum of this is, okay, converging to 0, right? So that's what we mean by a uniform sense. So regardless of the x value, okay, this difference is always converging to 0 in probability. So that's the uniform sense that we are talking about. You do need a little bit of theoretical assumptions, but usually they are satisfied. This uniform convergence requires some more involved probability theory tools, which we will not go over, okay? But an important fact is that such uniform convergence is usually true, okay? True in general. So here, why do we care about the uniform convergence? Because eventually, when we go about doing tests using EDF, essentially some of the tests are actually going to rely on this kind of computation. So essentially, what do you have? You have one EDF from one data set, another EDF from another data set. So if they both converge to the same CDF, then this bound you can use it. You can use this kind of uh, absolute value inequality kind of argument that okay, the two has a difference that's upper bounded by the difference the first minus the mean plus the second minus the mean. Okay, so that's going to be upper bounded by the two absolute values, which are directly related to this. Okay, so eventually in tests they would just calculate the function differences and then they look for the biggest possible difference, which is the supremum right here. So that's the reason. So we will get into those um, very soon. But before that, there's a very important topic we need to cover. So which is what's called the inverse of a CDF. 2.3. So inverse of a CDF is an important topic because it actually relates to constructing a random variable from a uniform random variable. So let's see. Let X be a continuous. Here we assume that this random variable is continuous. Okay, with CDF cap f of X. Now let's define a uniform random variable. Let we call it U. Okay, over the interval from 0 to 1. So this is very important. Okay, so remember the underlying assumptions. U is uniform over 0, 1. Now define a new random variable. Let's denote it as W, which is F inverse of cap U. Okay, so we have random variable X, okay, with a CDF. Now we have its inverse. Remember why it has an inverse. It's continuous, right? So it's continuous random variable. So the CDF is actually mm, there's no jump. So it's of course monotone, but then you would be able to inverse okay the CDF function. So now what's gonna happen here? Where of course F inverse is the inverse of the CDF. Now, how do you think W would relate to your random variable X? This is going to be very interesting. To understand W, let's do some calculations, okay? We examine its CDF. Let's denote it as cap f of sub W, okay? So this is the CDF of my random variable W. So cap f sub W of little w, okay? This equals to the probability, just by definition. This is, we have the random variable cap W. So we have the input little w. So that's my upper bound for the event of, within the probability, okay, within the CDF. So now, uh, if that's clear, we do the substitution, okay? So W is F inverse of U, right? So it's going to be P of F inverse of U. That's equal to W. All right. So remember, f is invertible and is monotone. Okay. So f is a CDF function. Okay. So it's increasing. Right. So now this equals to the probability of u less than equal to. So yeah, let me make sure that everything, if it's capitalized, it's then capitalized. If it's so yeah, that's u capitalized, and the w is lowercase. What's this? Uh, so this is u less than or equal to f of w. Okay, so I apply cap f on both sides. All right. Okay, so now remember, u is what? U is a, uniform random variable. Okay, and kapf is CDF. So this value is actually between 0 and 1. All right. So this tells you okay, I'm able to calculate the probability of this with the uniform random variable. That's easy, right? Because you're integrating from 0 to my upper bound of this is uniform. So this is little du. That's it. Okay, so uniform on 0, 1, right? So the PDF is going to be 1/1. Okay, for the entire interval. So what's this? This is actually u. So one, okay, the antiderivative is just u. Okay, we now talk about the random variable. Excuse me, the letter. Okay, the argument is u. So now we do the difference of f of w and 0. So clearly this is cap f of w. All right, does it make sense? So this calculation is nothing but using the definitions from before. So we started with what? We started with the CDF of W, okay, which is F inverse of U. But now we end up with this, okay? So this tells you the random variable W, cap W, and the original random variable X, they, although are defined possibly in different ways, but they have the same CDF for every W value. Okay, so they are exactly the same. Okay, in terms of CDF, this means excuse me, F sub W of little w equals to F of W for all W, which implies that the random variable W has the same CDF as the random variable X. Okay, it's the same. So let me highlight this. The same CDF. So this means what? This means, so sometimes your random variable X can be complicated, right? But then, as long as you know your F inverse, you'll be able to generate your random variable using this composition. Okay. The uniform random is easy, right? So drawing a number between 0 and 1 uniformly. So that's an elementary random variable that you can construct. Then, as long as you know F inverse, then you can construct W as composition, and then W follows the same distribution as your X. Okay, so even though X may be complicated, but as long as you know these components, then you're done. So this leads a simple way to generate. Okay, to generate a random variable from F, as long as we know what F inverse is. Okay. So step one, generate a random variable u from the uniform distribution between 0 and 1. And second step, feed u into function f inverse. Okay. This resulted random variable, random number f inverse of u. Okay. Has a CDF being cap f. All right. So this is a very good observation. That's much more helpful, okay, much more powerful than we could think. So sometimes you may feel that okay, there's a random variable that how do we generate it? So this is the way. So you start. So basically, as long as you know sufficiently well about your distribution that you want, as long as you know F inverse, okay, you can do the composition like this. So which is a little bit so this is a very interesting result. Okay, that's utilizing the inverse of CDF. Hmm. Another result. Okay, another related result. Consider a random variable v that's f of x. Okay, so here notice it's a little bit special. We have random variable x from before. Okay, but we are getting the composition. We have the random variable x, but we plug it into the CDF of cap f. So let's see what gets us. Okay, where f is the CDF of cap x. So you compose your random variable cap x into your uh, CDF function. Then the CDF of this v is the following. uh, Cap f sub v of, let's use little v to indicate the realization. Yeah, let me quickly finish this line before we end the class. Okay, so it's going to be probability of random variable v that's equal to little v. So now we substitute. Okay, so this is cap p. So the probability of, now we substitute, this is going to be cap f of cap x that's equal to v. Okay, so now what's this? Remember, this is the cap f. So we can take the what we can do here is to relate to the random variable. So remember, f is invertible and monotone. So take the f inverse to both the left hand side and right hand side. So this becomes the probability of x less than or equal to f inverse of little v. Okay, so the right hand side is a scalar, the left hand side is a random variable. Okay, so now remember what this is. We have cap x less than or equal to some scalar. This is the uh relating to the CDF, okay, of the value on the right hand side. And you see, okay, f and f inverse, they are composed. Okay, so that gives you v, okay, between 0 and 1 for any v. Okay, so this tells you what? This tells you if you do this composition, actually you get the uh, uniform random variable. That's your v right here. Okay, therefore v is actually a uniform random variable over the interval from 0 to 1. All right, so let's end the class of today and let me know if you have any questions. But